This is Wang, and you can call me YK Wang. I'm a senior lecturer at the University of Technology Sydney, Australia. My school is School of Computer Science, Faculty of Engineering and Information Technology, and I also belong to Australia Artificial Intelligence Institute, which is the largest AI institute in Australia. Today, my research topic is about human autonomous car teaming, a motion sickness study. So let's start the presentation. Yeah, human autonomous car teaming. As we may know, autonomous car will come into our daily life very, very soon. And we can see the autonomous car system is mature, is more and more mature recently. And we can expect the autonomous car will replace the driver in the near future. The other factor is Industry 5.0. The core concept in the Industry 5.0 is the cooperation between human and the agent. Combine the autonomous car in the Industry 5.0, we can expect the human autonomous car teaming is one hot topic. However, there is a lack of a high-resolution, real-time human-in-the-loop approach. On the other hand, 1/3 of Americans experience motion sickness. This is the report by the NIH. So combine the human autonomous car as well as the motion sickness. We would like to investigate the motion sickness study in the autonomous car teaming. And the other motivation is there is few systematic way to estimate motion sickness in the autonomous teaming system. There are 3 different systems which are related to the motion sickness. The first one is the visual system. The second one is the vestibular system. The third one is proprioceptive system. So the first one is the visual system. Yeah, as we may know, the brain receives visual signal from our eyes, and as the visual information is conflicting or mismatching the signal inside the human brain, and the human brain got a confusion with the visual input or visual stimuli, the human may experience the motion sickness. The second one is the vestibular system. According to the report or research, the researcher point out that blind people also feel motion sickness. So based on this finding, we can say the motion sickness is also associated with the vestibular system, and the vestibular system is well known for the balance. The third one is the proprioceptive system. Inside the proprioceptive system, muscles, ligaments, and the tendons are used for motion detection or motion sensing. So the information from this system will then deliver to the human brain. So if there is any confusion inside or between the proprioceptive system and the human brain, the human may also experience the motion sickness. So in the short conclusion, the motion sickness is highly related to the visual system, vestibular system, and the proprioceptive system. And like what I said earlier, the autonomous car or the car motion sickness is one big issue in the car industry. So some world-leading company also try to cope with the motion sickness. For example, Benz is investigating the seat position and the motion sickness. On the other hand, Jaguar also delivered a new technology to cope with the motion sickness. For example, the navigation system will only deliver the auditory-based information rather than the visual information. as you may know, the visual system is related to the motion sickness. So if the driver can reduce the visual information, it means the motion sickness can be regulated. The other hand is the seating position will be adapted to fit the current driver's position, or the seat will be adjusted to a more comfortable position. And the inside temperature will be also adjusted. But this kind of the technology is only based on the sensing or the road information by the camera or some kind of sensor. Or the other step is the questionnaire from the driver or passenger is used to evaluate the motion sickness level. So the drawback is the human is not in the loop for the estimation of motion sickness. So the question is how to explore and identify the levels of motion sickness individually and accurately in the human autonomous car teaming system. Biosensing would be one good way, like what we discussed earlier. The human brain may play one important role during the motion sickness. And we also know the questionnaire is widely used for estimation of the label motion sickness. However, the questionnaire is hard to get the continuous data. We can only get the discriminated information, and sometimes the participant, the driver, may forget to provide input for the questionnaire. The second one is we may also rely on the camera. However, the environment light or the illumination may be also one big factors for the quality of recording, and the camera may also lead to the privacy issue. So biosensing would be one good way to measure the level of motion sickness. The good thing is it's non-invasive, because for example, the wristband or Verizon EEG band in the market. Based on the biosensing, we can get a comprehensive assessment for the level of motion sickness, and we can also use this kind of biosensing technology to provide the individual analysis as well as an assessment. So this is one of our previous study. In the beginning of the experience and at the end of experience, there are two strength lengths, and between these two strength lengths, the participant will experience the continuous curve in the tunnel. The scenario like what you see in this picture. So the figure B shows the continuous change of level of motion sickness. This line indicates the starting point of the curve, and this line indicates the end of the curve, continuous curve. So we can see from the beginning of the curve to the end of continuous curve, the level of motion sickness is monotonically increased. And at the end of the continuous curve, we can see the level of motion sickness is reduced. And this is the scenario inside of the experiment. So according to our finding, the theta activity in the frontal region is monotonically increased as the level of motion sickness is increased. So we can say the frontal theta is a positive associated with the level of motion sickness. The following study is the motion sickness level between driver and the passenger. So in this study, we ask the participant to have two continuous recording. The first recording is the driver session. The second recording is the passenger session. So according to the result, we can see the passenger will experience the higher level of motion sickness, and we can also find the stronger frontal theta activity from the passenger section. This study is this experiment is conducted inside the VR scenario. So we use the motion capture system as well as the brain signal recording to capture all physiological change. And inside the VR scan scenario, we provide the translational gain labels to induce the motion sickness label. So 1x to the 10x represent the translational gain label. So the black curve represent the average value of the reported motion signal across all participants, and the green curve show the reported motion signal level from the non-motion sickness participant. So the red curve show the reported motion sickness level from the motion sickness group. Note for your reference, we categorize all participants into the motion sickness label group and the non-motion sickness label group. So this is the reason we can plot the red curve and the green curve. So the ongoing study is the human autonomous car teaming. So we just got a new motion platform here, and we are designing the motion sickness scenario. So inside the scenario, we would like to deliver one autonomous car scenario. And inside the scenario, we would like to integrate all physiological signals for physiological signal recording, including the brain dynamics, eye movement, heart rate, and the multiple physiological signal from the wristband. And our goal is to do the real-time data synchronization, and then we can do the real-time assessment for the motion sickness by the single or multiple physiological signal. And the third goal is to regulate the motion sickness in real time for better human autonomous car interaction or teaming. Yeah, so this is my team. Thanks for your listening. And if you have any question, feel free to drop email to me. Thank you.